2-week experiment, so we'll do first part this week, and then when you come back for fall break, we will be finishing it. As I warned you of last week, though, for your pre-lab, and we'll talk about this a little bit more detail here in a minute, you want to have the entire experiment in your pre-lab. So you do one pre-lab for experiment 7, and you want that completed before you come to class this week. So make sure you have the pre-lab for all of experiment 7 for lab this week. You'll have a quiz as always. Your experiment 4 report sheets and positive work notebook will be due. Some people it's due this week, some people it's due next week, so check with your lab prof on that one. Next week, it's fall break week, yay. So we aren't here on Monday, so we won't be here on Monday. We also don't have class on Tuesday, so we don't have lab next week. I'm too excited. So on Wednesday, which is Monday's schedule, which is very confusing, we don't have pre-lab lecture next week. So go to your workshops for organic lecture, but there is no pre-lab lecture next Wednesday. For next week for open lab, because we don't have lab next Thursday, we've got a modified open lab schedule. So Wednesday, we're open regular time, 9:30 a.m. to 3:30 p.m. Thursday, we're open 9 a.m. to 5 p.m. for open lab. And then Friday, we're open from 9:30 a.m. to 3:30 p.m. Regular lab schedule again. Okay. Also, you should have gotten back your notebooks, or very soon we'll be getting back your notebooks from your lab prof with experiment 3 graded in it. You will be rewriting the conclusion for experiment 3, and that is due in a couple of weeks. That is due the week you come back from fall break. So make sure you look over your corrections before you come to lab this week so you can ask questions, because when you see your lab prof again, it will be due. All right, lots of announcements. Okay, so today, let's talk a little bit about experiment 7. Then we're going to have a general discussion about polymers, and then we'll talk about specifics for this week. So, like I said, this week we are doing part 1 of experiment 7, but what I'm going to do right now, so you know where we're heading, is I'm going to go through all of the reactions that we are going to be doing for experiment 7. So there's 3 reactions involved. We are starting with, this week, ethylbenzene. And you are going to use N-bromosuccinimide, which I'll show you the structure of here in a minute, benzoyl peroxide, and hexane, reflux, and what you want to make is bromoethylbenzene. The reaction for this reaction, or the mechanism for this reaction, follows a radical mechanism. So it's a free radical, benzoic bromination. And so we'll go through this mechanism in more detail so you know what's going on this week. Then, when you come back in 2 weeks, we're going to be starting from your bromoethylbenzene. We're going to use quinoline and, again, more heat here. And so this is our step 2. This is a dehydrohalogenation reaction. So what does that mean? If we're dehydro and dehalogenation, what are we taking off? A halogen, and we're losing a hydrogen here. So what you get is this. You'll get styrene. Okay? Then we're going to take our styrene, and this will also happen in 2 weeks. We're going to use AIBN in a minute here. I'll tell you what that is too. And this time we're in toluene, more heat, and our step 3 reaction is a radical polymerization. So we've got 2 radical reactions in this sequence. Running out of room here, but radical polymerization. And so we're going to form polystyrene in the end. And this, we'll get into more detail in 2 weeks about this, but our start of our polymer comes from our AIBN. So let me draw a couple things up here so you know what I'm talking about. So first of all, benzoyl peroxide is part of our first reaction. This guy here. Then we've got NBS or N-bromosuccinimide. That is also part of our first reaction. And then in our last reaction, we have AIBN. So that's this guy here. And this guy's kind of the tongue twister of them all. So it's easier to say AIBN because otherwise it's azobis, isobutone, butyron nitrile. So we'll go by AIBN. And like I said, this is part of the third step. So these two, part of your first step reaction, we're going to use these guys this week. This is part of the third step reaction. And so the goal of this whole experiment is you're going to be making a polymer. And we will talk about in a couple weeks in 2 weeks, how you're going to actually analyze your polymer as well. So I want to go over just some general information about polymers before we talk about this week's specific reaction. So polymers are really large, giant molecules. So far we've been talking about really small molecules, monomers, just one piece. You could link 2 monomers together, get a dimer, or link 3 of them together, get a trimer, or link multiple of them together and get a polymer. And so that's what we're going to be doing in a couple weeks with our styrene. So polymerization is the chemical process of linking the monomers together. Right? And so a little bit about the history of polymer use. First of all, they started in the early 1800s using naturally occurring polymers. People were using natural rubber, silk, other types of polymers for things that they needed them for, tires, silk for clothing, things like that. So first it was just using what was out there. Then people got the idea, well, why don't we just try and chemically modify what's out there and make it better? So things like vulcanizing natural rubber came about. And then people looked at, it's a really kind of a pain to go get the rubber out of the rubber tree or get the silk from the silkworm. How about we go and try and make this naturally occurring polymer ourselves? And so that was done for a while. And then people decided, well, instead of just making the ones that occur in nature, let's just make other ones that don't occur in nature. And so that is what we've a lot of what the polymer industry is now is making polymers that don't occur in nature that have a lot of unique properties. And so things were, going along, developing in the polymer industry. No real major things driving it. It was just occurring to make things a little bit better. Then we were brought into World War II. So December 7th, 1941, completely changed the polymer industry. So the bringing about of World War II was a huge boost to the polymer industry, because all of a sudden we needed these resources that weren't so readily available, and we needed a lot of them, especially rubber. And so they needed a way to make rubber that didn't come out of a rubber tree. And so then the polymer industry took off from there. And so if we look at a comparison of natural rubber to vulcanized rubber and how that became better by just changing the natural rubber a little bit. So natural rubber hang out as polymer strands all linked together. Then you stretch it. Then after it would come back together after stretching, it wouldn't really hold its form completely. It would mostly, but it'd be a little bit stretched out. So they needed a way to improve that, especially for tires. You don't want tires to become a little bit stretched out as you drive. And so what they looked at was how to make that rubber hold shape. And so they started the vulcanization process, where they would, with the rubber strands, add crosslinks between those rubber strands to help them hold together. So then when you'd stretch out the rubber, it would come back again to the same shape after you stretched it, instead of being a little bit stretched out. So this, just vulcanizing rubber, was a huge boost in the polymer industry and a huge improvement in the polymer industry. And then, like I said, then they all of a sudden, countries, including ours, needed a supply of synthetic polymers and synthetic rubber. So with the polymers, when we talk about their macromolecular structure, there's multiple ways they can be linked together. And so if you think about different types of polymers that are naturally occurring, like RNA or DNA or proteins or polysaccharides, there's different ways and different structures that all of those polymers take on. And when you're talking about polymers, you're usually talking about, instead of, we've been looking at things that have like tens or hundreds of grams per mole molecular weights. We're looking at thousands or 100,000s size molecular weights when we're talking about polymers. So these are going to be huge molecules linked together, all acting as one big macromolecular structure. So one way that they can be linked together is just linearly. So you get this really long polymer chain. They could be linked, have one long polymer chain and then branches coming off. So this is the branched architecture. You could have a center, a common center that everything branches off of. So that'd be the star architecture. You could have the cross-link network like I talked about with the vulcanized rubber. So you've got linear polymers in there, and then all those linear polymers are linked together to provide more strength and support. And then you could have something like this dendritic polymer where you've got this core and then huge amounts, instead of just the star where you have a few linear polymers coming off of it, you've got huge amounts of polymers branching off, and then from their branch, they're then branching off more and more and more to make this whole dendritic structure. Another thing you can do is, instead of having the just repeating one molecule over and over again for the polymers, you can have multiple molecules repeated, and so you can change the properties of the polymer by how what you use as copolymers, so using more than one monomer together, and how you link them together. So you could just put a couple things together and have them linked randomly, not really have any general structure to how they are linked. you could link them in big blocks of monomers linked all together. So an example of this is Saran wrap is a block of different polymers, and all those blocks are linked together. Or you can alternate one another back and forth, back and forth, back and forth. So this is the type of copolymer that nylon is. Whoops. It's a linking of the two molecules that are involved in nylon going back and forth. And so if you remember from Gen Chem, they did the nylon. Actually here, if we look at, first of all, at Saran wrap, Saran wrap is ethylene and then acrylic acid put together. And so from the ethylene, you get the strength of the Saran wrap, and then from the acrylic acid, you get these acid groups coming off, these OH groups coming off, and that's what sticks to glass. That's why Saran wrap sticks to things, is because of these OH groups. So you've combined the strength with the stickiness to get the Saran wrap, and it's blocks of these are put together so that you have the strength in the right place, and then you want, of course, on the outside of it to be sticky, to stick to things. Okay. With nylon, you're taking a dipolyl chloride and 1,6-hexane diamine, and you've got this two-phase system, and then they mix right at that interface of the two phases. And so then you just get an alternating, at that interface you get the alternating of the two different molecules together. And so this is one chain of the two molecules, and then it's just constantly repeated over and over again to get the nylon. And that's what, combining the two of them together is what gives the strength of the nylon. And so nylon was another huge, creating nylon was another huge advance in the polymer industry, because before that they'd mainly been using silk, and so they needed nylon for all sorts of things besides just ladies' nylons, but you needed it for rope and all sorts of things that nylon is now a part of. So looking at the polymers, we're going to use, in a couple weeks, we're going to make our styrene. So we've got this molecular weight of 104.15 for just styrene. And then when you put it together to make polystyrene, you make huge molecular weights, 500 to 400,000. Usually, commercially, it's somewhere in the 50,000 to 150,000 grams per mole for a molecular weight. So really large molecules or macromolecular structure for the polystyrene. So the polystyrene you're going to make is probably in the range of like 5 to 10, 15,000 molecular weight for what you'll make in lab, because we're not going to do a whole lot to control and make it a very large molecule like they do industrially. And so the properties that polymers depend on are what is their molecular weight, how big are they, what is their chemical composition, what macromolecular shape do they take on, and then how are they processed to get get the one type of polymer out. So there's specific things with each type of polymer you have to do in the processing and the making of the polymer to control your chain length and control what is produced out of it. And so looking at what we're going to do this week with the first reaction that we have, we're going to take our ethylbenzene and we want to brominate it. Now we could just take, you can just buy bromine and we could just drop bromine right in there, but we don't want all of the bromine available all at once. We want the bromine to be slowly forming and then being used up as the reaction goes on. We don't want that bromine source there all at once because of the type of mechanism it is, because of it being a radical mechanism. And so what we're going to use instead is the NBS. So is the N-bromosuccinimide. Now we also, like I told you earlier, we're using benzoyl peroxide. And so our benzoyl peroxide is our initial source of radicals. So being that this is a radical reaction, we're going to have a radical chain reaction, which I'll go over here in a minute. And so we need that source of radicals. So that's what that benzoyl peroxide provides for us, is that initial source of radicals. And then again, we're in hexane and heating this up. So our benzoyl peroxide is easily broken apart just upon heating. And so as you heat up this reaction, all of a sudden this benzoyl peroxide will break apart and get your radical chain reaction going, okay? And so it's this bond here that easily will break apart. And you'll get that guy out of it. To be complete, we get 2 of them out for every benzoyl peroxide. And so here is our product. Think about here for a little bit. We're going to come back to this. Why do we add there? Why don't we get bromoethylbenzene where we have our bromo group on the terminal methyl group instead of on the methylene? What is going on there to brominate at that position? And then, like I said, our NBS is our source of bromine, and so it forms this nice steady source of bromine that doesn't ever build up a huge concentration of bromine. And so as it reacts, first we need a source of HBr, and I'll show you in a minute where that comes from. Then what you get out of it is just succinimide, okay? So we have N-bromosuccinimide. As it reacts, you just get succinimide. And the bummer about this guy is it's a very nice yellow-white solid. It looks like it should be your product for the reaction, but in the end, you don't want it. So in the end, we're just going to put it in the organic waste. So when you're done with this reaction, you are going to cool, so you're going to reflux the reaction, you're going to cool it down, and then once you've cooled it down, you're going to gravity filter off this succinimide, and then you will be, you want to keep the filtrate. So the liquid you keep, the solid goes into the organic waste, and then you will do a simple distillation to get rid of your hexane, and then you'll have your bromoethylbenzene. So just don't be thrown off by the nice white yellow solid that you will be forming. You don't want it, okay? Now another thing you have to be careful of with this reaction is it does take heat to get going, but you need to watch it. So once you get it refluxing, don't just walk away, because it's very easy for this reaction to go from refluxing nicely to all of a sudden generating its own heat and refluxing very quickly, okay? So keep an eye on what's going on with the reflux and make sure that you adjust the heat appropriately. As it starts getting a little bit more vigorous in its refluxing, you may want to turn down the heat a little bit, but remember, you want to reflux for the entire hour that it tells you to, so don't turn it down so much that you stop refluxing, okay? But be really careful with the reflux not to just walk away and let it do whatever it's going to do on its own. You don't want hexane then leaving your condenser. Another thing to be really careful with is benzoyl peroxide and peroxides in general are explosive, so you don't want to just leave it around. We keep it in the freezer up until you use it. Take what you need, and then make sure that all of the benzoyl peroxide that is left around is cleaned up well. You also don't want to grind the benzoyl peroxide or crush it with your spatula because you don't want it taking off on you, okay? So when you are ready to add it to your reaction, so you've got your NBS, you've got your hexane, you've got everything ready to go, you've got your ethylbenzene, when you're ready to add it to your reaction, then weigh it out and then add it to your reaction. You don't want to just let it sit out and wait for 20 minutes while you get everything set up, okay? All right, so let's talk about all of the steps involved in the reaction itself. So here's our formal radical reaction. Elimination of ethylbenzene. Okay, with every radical reaction, what is the first step? Initiation. And so what we get from over here, I got to show you the rest of it there, is Br2, all right? So this generates our Br2. So once that is generated, then we have our Br2 with either heat or light, and we're heating the reaction, so we've got what we need. We're going to get our bromine radicals. So then what happens after initiation? Propagation. And so then we've got our bromine radicals, we take our ethylbenzene, whoops, getting ahead of myself here. And then you're going to react this with a bromine radical. And remember, when you're showing radical reactions, the type of arrows that you're showing are half arrows. And so from this, we get our radical of ethylbenzene, plus we get HBr, and this will be used with the NBS to get our Br2 that we need back up there. So the second step, so this was our first step, propagation. Our second step is then we've got to take our ethylbenzene radical and we need to react it with bromine. And then we will get the product that we want. So again, remember our radicals, and we've got this radical and this radical coming together. So we've got our product, and then our bromine radical that we can use back up here again with more ethylbenzene to get regenerate our ethylbenzene radical. So looking at this, I asked you earlier, why do we brominate at the position that we do with the ethylbenzene? It's the benzoic position, and so why is that important? Why is it more stable? because of the resonance structures, right? So it's stabilized by resonance. And so as practice, you might want to go through and see how many resonance structures you can draw of this radical. But this position is really important because of the resonance structures and how it is stabilized. That's why we form this radical. We don't form a radical here. And what else is in the reaction mixture that you could form a radical with that you don't? What's your solvent? Hexane. That's very similar to ethylbenzene, right? But you don't brominate the hexane either, okay? So it's really important what is going on with that benzoic position. That is why we get what we get out of this reaction, okay? And keep in mind that benzoic position because it comes in handy multiple times in organic chemistry in general. So then what do we have after our propagation? Termination. And so the combining of any two radicals is our termination. And so with this whole set of steps, the reason that we need the benzoyl peroxide is because our bromine source is the NBS. Well, we don't get the NBS to form bromine until this step here. So we need a source of radicals to get this all started. And so that's what the benzoyl peroxide does, is it's just a source of radicals to get everything started. Okay? Now, there's a couple of things that you're going to use to test that you have made your bromoethylbenzene, okay? One of those is the density versus water and ethylbenzene test. So you're going to have two test tubes, okay? You're going to put in those test tubes either a half a mil to a milliliter of water, no more than that, okay? In one of those test tubes, you're going to put ethylbenzene in that test tube and see what happens with it relative to the water. So what do you expect would happen with the ethylbenzene? It's going to float, right, in the ethylbenzene. Okay, so then you're going to have another test tube, another half mil to milliliter of water. You're going to put a couple drops of your bromoethylbenzene in there. What should happen? It should sink, right? Because halogenated compounds are usually more dense than water, right? Versus the unhalogenated compound. Well, one thing that may happen is, remember, we've got all this hexane in our reaction. We've got to do a simple distillation to get it all off of the product. If you still have some hexane present, then it's going to throw off your results for this density test, okay? Because there'll be enough hexane in there that makes the bromoethylbenzene not so dense, all right? So make sure with your simple distillation that you push the simple distillation to get all of the hexane off of your compound, okay? That way it'll make the density test work out better. The other tests that you can use are, first of all, you can use a silver nitrate test. So if you guys remember, silver nitrate test from Gen Chem, from Qual and Gen Chem, and it would react with other species that contained halogens and make a nice white, yellowish kind of solid. The same idea here. So we've got our bromoethylbenzene. And we're going to react it with silver nitrate. It's an ionic species. And this is all in ethanol. And so then what you will get is we will actually form our cation of our bromoethylbenzene, and then we'll form some silver bromide solid. And so you'll get this white yellow precipitate. And so you should see that white yellow precipitate crash out. Now, it's not like ionic species reacting with ionic species. So we're not silver nitrate with sodium chloride. So it does take a little bit for the reaction to take place. So just give it a minute or two and watch it, and you should get the solid silver bromide to crash out, okay? But it may not be as instantaneous as it was in Gen Chem lab. But this reaction does occur more quickly than, say, we just used like bromopropane or something like that, because of this benzoic position being so reactive and having that bromine at that benzoic position. Another thing that you could do, especially if your density test doesn't work out so well, is we've got our Beilstein flame test. And so you could test to make sure that you now have gone from something ethylbenzene that doesn't have a halogen. You test your product from this week and then get a positive flame test, then you've got confirmation that you do have a halogen, okay? So the two tests that your lab manual mentions is the density test versus water and ethylbenzene and the silver nitrate test. But if your density test is off, then you could also confirm with your Beilstein flame test, okay? Now for your compound, because of what it is actually really reactive. The bromoethylbenzene is fairly reactive. And we've got to make this compound last for 2 weeks and be stored for 2 weeks so that you can use it in a couple weeks to form styrene. So you don't want it reacting and forming anything else, okay? So you want to store it in a small, clean, dry vial. So use as small a vial as your compound will fit in, okay? So you're starting with 5 milliliters of ethylbenzene. So ideally, if you get all the hexane off, your product should fit in a 7 milliliter vial, okay? So go for the small vials first and see if it'll fit in there before you aim for the big vials. But you want the small, clean vial, you want it to be dry, and you want to cap it tightly and stick this in the back of your lab drawer so it's away from light, because just like heat, light will make it react. So it's stored in the dark for 2 weeks, and then hopefully we'll have some success of it not completely decomposing on us before we use it 2 weeks from now. The other thing I would do is take careful notes of observations of what it looks like, because it may look different now than it does 2 weeks from now, okay? So this is how we're going to store it. Before we put it away, what we need to do is you need to know the mass of the vial and cap, and so you can calculate yield. You also need to know volume of the product. So you need mass and volume of your final product. The mass you can get by knowing what is the mass of the vial and cap empty, put your product in there and weigh it after you put it in and find out the difference. The volume of the product you need to measure before you put it in your vial, okay? The reason that we need to know the volume is there is, like pretty much everybody will have at least a little bit of residual hexane left on your product from this week. Next, or 2 weeks from now, when we go to make the styrene is formed in a fractional distillation. You're going to use your all-in-one simple distillation apparatus that you used last week for your unknowns. And the styrene is actually formed by it distilling off of the bromoethylbenzene and quinoline mixture. Before your styrene distills off, your hexane that's left is going to distill off. And so you need to know this volume. So then you can combine it with the volume that you get from 2 weeks from now for the hexane to figure out how much of this was still hexane so you can accurately calculate your yield, okay? So that's why you need the volume. Now, we talked about we're going to complete the pre-lab for this experiment all at once. So you're going to have this entire pre-lab in your lab manual before you come to lab this week. A couple things that you need to know. So first of all, we've got 3 reactions involved. We've already gone through that. Because of that, and because it is a 2-week experiment and there's so much involved in this report that you'll hand in for experiment 7, this guy is worth 75 points instead of 50 points. So you want to do a really good job with your pre-lab, with your experimental, with your conclusions, okay? But it is 2 solid weeks of work, so you want to get credit for 2 solid weeks of work. So it is worth 75 points. So like I said, the pre-lab contains all 3 reactions, so you want the information for all 3 reactions. In that pre-lab, there's a couple things that you need to keep in mind. So we're going to show, in the reactions portions, you'll show the reaction for all 3 reactions. You'll probably need to do a flow diagram that somehow shows the 3 reactions, or the workup of the 3 reactions. Then you also need a yield calculation for each step, because there are 3 steps involved. So step 1 and step 2 will be a regular yield calculation like you've done. So regular theoretical yield, and then you would use that theoretical yield to get percent yield. So to do this in your pre-lab, you want to base this off of what your lab manual tells you you will be using. So calculate based off of what you're starting with this week, how much product you would have from that for this week, and then that product going into the second step, and what would be your yield out of the second step. Okay, so all of these calculations are based off of what your lab manual tells you you will be using, and based off of you using up everything that you make, right? For step 3, we can't do a regular yield calculation because it's really hard to figure it out with the polystyrene, because we're not going to have polystyrene that's all 1 molecular weight. And so what you're going to do is you're just going to calculate a weight percent. And so you'll show that you're going to use grams of polystyrene that you make are going to be divided by the grams of styrene that you put into that 3rd reaction times 100%. So it's just a weight percent is what you're calculating for yield for step 3. You're not calculating a percent yield, all right? Okay, questions with that? Yeah?
Is the quiz going to be over the whole experiment?
The quiz will be over what I have shown you today. So in terms of whole experiment, like that reaction sequence could potentially be involved on the quiz, or the mechanism, me telling you what type of mechanisms are involved, that kind of thing. The in-depth part is what I've covered this week, and then 2 weeks from now, the quiz you'll have will cover what I covered 2 weeks from now. Okay? Yeah.
So, do we need to show like the whole mechanism in the pre-lab?
It's a good idea to at least have, like, you need to show the reactions, but it's also a good idea to understand how those mechanisms work each time.
What about like the nitrate test? So nitrate test.
That, not so much. I mean, that one's kind of hard. You've got it's hard to show a mechanism for a covalent compound reacting with an ionic compound.
Pre-lab?
Pardon?
Do we have to put that in the pre-lab?
You should show that reaction in the pre-lab though. Yeah. Okay. So to help you guys out with your pre-lab, so the bonus for coming, let me sit down so you can see, is I have a partially filled out physical data table. So you want 1 physical data table for the entire experiment. And so I have here completed part of that physical data table for you. But it is only partially filled in, okay? So you've got all this information here. You need to fill out amount moles for all of these chemicals, And for the styrene methanol, you don't need dichloromethane anymore, but styrene methanol and THF, tetrahydrofuran, you need to fill out all of the physical data table, okay? But now you do have part of it for your pre-lab to help you get started. But do double check, make sure you can be my check to make sure I didn't leave anything out of that. Remember that you always want to show all the chemicals you're using as well as all the products that you are going to be making. Okay? And then once you have that, unless you have any other questions, I am done with lab lectures for today.